Thank you. Good afternoon, everybody. And today we would like to talk to you about how we solve the problem of social media influences detection, analysis, and recommendation using Apache Spark. So just very shortly about the company itself. Socialbakers was founded in 2010 in Czech Republic. And the product we have is a software as a service platform we call AI-powered social media marketing suite. And it allows you to do quite a few activities in regards to social media marketing. So you can analyze performance of your profile on Facebook, Instagram, if you are a big brand, how many likes you have in time. You can also construct and publish content into those social media networks. You can do some analysis of your audiences. And finally, the topic of this talk is actually the influencers. So we allow you to find and we recommend you influencers for your campaigns. For the purpose of this talk, influencers is only on Instagram only influencers. It's what we call business profile, or what Instagram defines as a business profile. So that's a specific setting in Instagram if you have a profile, which you say, I'm open for business. I'm open for sharing commercial content. I'm open for doing business through Instagram. And the last limitation is that you need to have at least 1,000 followers. So what's the use case we are solving for our customers? Basically, if you want to share some commercial message about your product or services you offer as a brand, as a company, you can do it the traditional way, where you publish an ad. Or you can actually start cooperating with someone who is well respected in some communities or is trusted by people. And here is an example. You might ask them to review your service or product you offer, and they might publish something like this, that they have reviewed the TV, and it's really amazing. So from the data perspective, the problem is fairly straightforward, to be honest. We have some unstructured data. Here is a snapshot of Instagram, what we call bio, of one Instagram profile. In this case, it's Gareth Bale, UK footballer. And this is the information, how it looks. He says he's a footballer, in Real Madrid. This is a piece of content he published. He publishes quite often, quite regularly. It's a big influencer. And in this, there is a picture of him doing a training somewhere, football training. So that's the unstructured data. And obviously, we want to convert it into some structured data. That means that we want to know the gender of the influencer, if it is a person, age, some kind of a bracket. We discretize the data, and what country he comes from or she comes from, and what are the interests. In this case, it would naturally be that he plays football. And finally, we want to put a search or recommendation engine on top of that. So in general, we are taking this about 100 gigabyte data set of posts and bios, and we want to process it regularly into structured data and allow our clients to search on that and give them some recommendations which influencers to work with. And basically, we actually solved the problem first. We use technologies that are quite heavily used in our company. That means JS, in this case Node.js, and Mongo, NoSQL database. But there were many issues with that. It was very slow. The whole data set, it took us about 5 days to process. It wouldn't scale well, so if we added more data or the complexity of the detection and recommendation become bigger, it would be very difficult to scale it. We didn't really have a good control over the solution in a sense that if we improved the algorithms of the detection, we couldn't compare how well we improved because we're overriding data in Mongo, so we didn't really take snapshots. And in general, some kind of analytics on top of the data set was troublesome because after all, Mongo is not an analytical database. So we needed a different approach to basically process this 100 gigabyte data set. So we kicked off a project we called Internal Influences on Spark. And let me talk briefly. The main of the presentation will be about this project. So the team that was solving the problem, that was myself and Jan and 4 other data scientists and researchers. We cooperated together with company Datacentrics. They have a stand downstairs, so please do talk to them, smart guys. And we were obviously supported by some other teams in the company. This was data teams, DevOps teams. So in general, I would say about 7 people was working on this project, on delivering the influences on Spark. So just to give you some timelines. We obviously started with Spark itself as a technology way before we kicked off the influencers on Spark. We started about a year ago in October 2017, so we kicked off Apache Spark POC. There were two major goals of this POC, and first one was answering question whether we need Apache Spark in the company, whether it will help us solve the use cases we have. And if it does, what platform we will use. We are AWS house, so for us, natural choice would be AWS EMR Spark, and we benchmark it against Databricks, which is a fully managed Spark, as you know. So during those about 5-6 months until February 2018, we piloted various use cases, ETLs, ad hoc analytics, simple ML models. Quite a few people had a chance to play around with both platforms and Spark itself. And after quite thorough evaluation, we decided to deploy Databricks as our platform for Spark. The major reason was that in general in our company, we tend to select managed services. So for example, we migrate from Mongo to Dynamo in case of NoSQL databases. And for Databricks, we were happy with the stability of the solution and of the platform, and there was nearly no DevOps work related. So the platform was released in February, and month after that, we kicked off the influencers on Spark. It started as a research project, as a data science project. So we wanted to see if those algorithms that were firstly created in JavaScript could work better in PySpark, and we quickly realized the potential of the technology, and we started developing the end-to-end pipeline on Spark, and we aimed mainly for scalability and performance of the solution. And it took the team 6 months to deliver the solution. So in general, it took us 6 months to onboard the platform, because the team I introduced on the slide before actually didn't have much experience with Spark, nearly none experience. Also was onboarding or learning Python, and yeah, 6 months. So I think it's quite good. And with that, I'll hand over to Jan, who will tell you more about the solution itself.
Thank you. Good afternoon. My name is Jan, and I'm going to talk about our implementation of influencers on Spark. From development perspective, Influencers is a search and recommendation engine built over a database of public profiles, their performance metrics and attributes. Public profiles, in our case, are public business Instagram profiles available through public Instagram API, having at least 1,000 followers. Performance metrics are also available through this API. These are numbers like number of followers or number of posts. And attributes are properties of users, profiles, or people in general, such as age, gender, or languages they speak. On the right side of the slide, you can see a typical Instagram profile enriched with these attributes and metrics. The attributes are not available through the API. We have to derive them on our side. And to do so, we've built a number of predictors. We can predict age, gender, languages, interests, and locations. Specifically in case of gender and age, we exploit a third-party API for image processing, but the rest is built and run completely in-house. Here I can show you an example of such predictor. This one we use for prediction of locations from text. It's a very basic version of extraction of entities from texts. It's basically a database of entities and expressions. Expressions are typically keywords or regexes, and we have more expressions for a single entity. And when we use it, we load a text. We scroll through the database of expressions, trying to find a match. And when we find a match, we load corresponding entity ID and entity. And now we know the text is about London in UK, and that London is a city. In this case, we use a database of 850 different locations, described with 26,000 expressions, written in 15 different languages. This was just one predictor. When we predict an attribute, we predict it multiple times. We combine different data sources and different predictors. And this way, we generate a number of base predictions. Then we collect these predictions, we combine them, we ensemble them using majority voting model, and calculate single, more accurate final prediction. At the same time, we also calculate a confidence score. This number says how much we believe the prediction is correct. But in this phase, we don't use the score to filter out less reliable results. We just predict all those attributes, calculate the scores, and send it to our recommender. Later on, when we recommend profiles based on a search query, we calculate a relevance score. This score is a weighted sum of full text search score, performance score, and attribute score. Here the attribute score is the important one because it's a combination of how well attributes of a profile match attributes of a search query, and at the same time, how much are reliable predictions of those attributes. So the confidence score mentioned on the previous slide is used to prioritize results. This way, we maintain maximum coverage of our database of influencers because we don't reject profiles with less reliable predictions. But at the same time, we maintain good experience for our clients because we always show results with more reliable predictions first. Here on the right side of the slide, you can see a diagram of what we have built. It starts with Instagram API Grabber. This is not part of the influencers pipeline. Influencers pipeline is built strictly on S3 and Spark. The Grabber is not. And the Grabber is used to search for new profiles on Instagram, to download them through the API, to filter them, and keep only those that are public and have at least 1,000 followers. It also caches these profiles. And then, when we run the influencers pipeline, the pipeline loads the data from the cache. It performs some basic transformations and buffering on S3. Then it applies the base predictors. It generates base predictions, basic analysis. It extracts some keywords, hashtags, and so on. Then it ensembles these base predictions. It merges all those analyses together and generates the final representation of every influencer's profile in our database. Influencer's profile is basically the original Instagram profile enriched with all those attributes and performance metrics. And in the last step, the pipeline loads these influencers and transforms them into two versions. One that is suitable for search. This one contains all those scores, attributes, weights, and so on, and is stored in Elasticsearch database. And second version that is suitable for being displayed in our product. This version contains profile photo, profile bio, and so on, and is stored in the MongoDB. Then when client uses our product, he or she can create a search query. The query is sent to the Elasticsearch. There all the recommendation happens. We send back list of IDs of recommended profiles, and the product can load individual profiles from MongoDB as needed. This pipeline is run once a week. We plan to run it more frequently, but right now it's just once per week. We run it on a cluster with 8 nodes, having over 100 virtual CPUs and almost 1 terabyte of RAM. Every time we run it, it processes almost 30 million profiles and over 20 million posts. Together, it's a little bit over 100 gigabytes of data in a form of compressed Parquet file. And the pipeline typically runs for 4 hours. Approximately 50% of the time is just transfer of data to the pipeline and from the pipeline. So those calculations run for 2 hours. And when the job is finished, we get some results. Right now we have a database of 27 million profiles or 27 million influencer profiles. 90% of them enriched with languages, 44% enriched with age, gender, interests, and location. On the right side of the slide, you can see a demography of our influencers. Obviously, it's 50-50 male and female, most of them between 18 and 34 years old, younger women, older men. Here you can see 10 most frequently detected interests in our database. It's top 10 for male and top 10 for female, but 7 of them is common for both genders, and only 3 is where they differ. It's music, sports, and physical exercise for male, and cosmetics, beauty, and motherhood for female. This is just top 10. We are able to detect over 300 of different interests. And here you can see a screenshot of our product. It's Social-Bakers Influencers. You can see a real search query on top of the screenshot and set of real results at the bottom. That's all from me, and I hand over back to Petr.
Okay, thank you. So basically what we want to share with you is the experience we had with onboarding Spark. I will just remind you that at the start of this project in March, the team itself has very little experience with Spark, just some simple ad hoc analytics, very little knowledge of Python, no experience with developing in notebooks. So yeah, how it went. So the lessons learned, we have accomplished the goal we had. So the solution itself is much faster. So as mentioned before, we are able to process it in a couple of hours rather than several days. And obviously it scales well, so we can execute this if we need to, and it will process faster. What is important, what we learned is that actually the 20% of the whole time we spent on the project was the smart stuff, the detection and selecting the right algorithms. But most of the stuff was actually spent on the data engineering. I guess that might be similar for some of you guys who actually deal with projects like this. And there is this conflict between data science, data engineering / software engineering. On the data side, we started this project pretty much as a data scientist project, prototyping, and then it evolved into this data engineering. And there were quite a few how to do that, right? If you want to have a scalable architecture. So after a while, we arrived to something what we call Social-Bakers Spark pipeline architecture, which is this diagram. So just briefly, we understand cluster as a container, which has environment variable, which defines the environment itself. So it's either development, QA, prod. And then on top of those yellow boxes on the left, these are libraries. Most of them are open source. We have one simple Python package we have developed ourselves, and these are obviously attached to the cluster when it starts, and we import them using the import command. Then on the right, we haven't refactored or moved everything into packages, Python packages, but we also have what we call classes notebook. So it's a notebook in Databricks which contains classes that are used in other notebooks. This one is imported using the run command. We have also moved all the configuration parameters like paths to S3, or we access actually through Metastore. So table names and various other parameters of the pipeline into a configuration notebook. This one is again moved, included using the run command. Then in the middle, the purple boxes is the pipeline itself. So we try to build modules that are responsible for a specific task in the pipeline, and they are independent from each other. From the left, you have, we extract the data from the source, then we do some pre-processing, then the smart stuff, the detection of those various attributes, and then post-processing, and then we start pushing the data into the destination, which in our case is Mongo and Elasticsearch. Then there is a master orchestration notebook, which is a now fairly simple notebook, and this notebook, what it does, it uses the Databricks proprietary feature dbutils notebook run, and runs the specific notebook with parameters it needs to run with. As I said, S3 is our lake where we store most of the data, and it is accessed through Metastore. So this is what we have now. Few more points. What we are quite happy now that each of those purple notebooks, or major stages of the pipeline itself, they persist data into S3. So we have snapshots of all the major parts. I know it takes time. It's a problem with performance sometimes. It slows down the pipeline. But if someone from the business or some customer challenges the data, we can fairly easily tweak it or find where the issue happened going upstream, right? So all these data sets can be quite easily with AWS Athena. And then when someone says, okay, this influencer was detected as, I don't know, footballer, this is not correct, why it has been detected like that, so we can debug it within minutes on this data set. Yeah, and one warning, at least from our side, deployment of Spark into existing infrastructure was not straightforward for us. The major issues we hit was with Mongo. We were overloading the database both on reads as well as writes. So we had to deal with batching, how much data we will send there, and then reduction. We had to reduce the parallelism, and we actually had to write our own notebook that it is only solely responsible for writing data into Mongo based on the data frame we sent to it. That's this, and yeah. So the last point is the continuous integration and continuous deployment. For the notebooks, we still haven't fully resolved this issue. At the very first version, most of the code was just in Databricks, and we have written our own simple Python tool that extracts the data or the notebooks from Databricks through the workspace API and pushes them into our GitLab. There, the developers merge the changes, and they can use the same tool to actually publish it back into the Databricks. So now the ownership of the code is on side of our infrastructure, which we really need, and it allows us for multiple developers as a team work collaboratively on notebooks and merge changes. So that's pretty much it. And yeah, if you have any questions.
You said you were on AWS AMR and then you moved to Databricks. No?
No, we piloted both platforms at the same time. So we kicked off in October 2017. We had EMR plus Zeppelin and Databricks as a paid trial. And for those 3 months, whoever wanted could pilot those use cases. We had ad hoc ML ETLs on both platforms. And then there was a collective decision as a team, about 12 people, what we like more, and that will be our Spark platform.
Any comparison results which you can share?
So the major reason why we selected Databricks is for the stability. It was much more stable than EMR. We were hitting issues with EMR. It was freezing where multiple people were running jobs, and our DevOps department is fairly small. So they didn't have any knowledge of Spark, so they actually couldn't resolve these issues. So that was one thing. The other thing was that in Databricks, you can provision cluster per job, right? So you have a job, you attach the right libraries you need, and kick it off, it processes it and kills the cluster. I couldn't imagine that this level of separation of jobs per cluster we would be able to achieve on EMR. And in general, the feedback from the developers was that and analysts was that they actually liked the interface, the UX of Databricks. They felt more productive. So these were the 3 major reasons.
I would have one question regarding the issue with overloading Mongo, because we are using it as well. So the issue was due to too many requests on the Mongo, and when you started batching the requests, it improved the performance? So
basically, it was a problem that there were too many processes fired off by Spark. If you have 16 CPUs, it started downloading 16 processes from Mongo, and it was simply overloading the database. So we had to kind of decrease it, and our level was 4 to 6 that the production databases actually were happy with. And what we did to prevent the Spark tasks to be too large, we actually batched it and then, for example, the 100 gigabytes, you batch it into 10 gigabytes, and then you decrease the parallelism to 4, so each task goes about 2 gigabytes. So that's how we resolve the issue. I don't know if it's the best way, but it helped us.
Thank you very much.
Any other questions?
Thanks. Is the 4-hour runtime the optimal time for your platform?
Sorry, say it again?
The 4-hour runtime per week, is that the optimal time for your platform?
To be honest, quite a few of our execution plans are not optimal. We know they are suboptimal. So we are actually looking on this right now and trying to remove shuffles and all the unnecessary stuff. But there is a part, as Jan said, about 50% of the whole pipeline is just extracting data and dumping them into the destinations. So there is very little room to optimize that now. Maybe going forward when we digest from S3 directly, maybe someone dumps the data in S3 and we can digest it directly from S3 rather than from Mongo. But for the Spark part, we are optimizing it, and we are actually preparing a release of a new version of this pipeline in coming weeks.
Thanks.
All right, great. Thank you so much. And please remember to rate the session afterwards. Thanks.
Thank you.